Assalamualaikum warahmatullahi wabarakatuh. My name is Fahmi bin Sadun. Matric number B0819100079. And my friend,
Assalamualaikum, my name Haris Hakimi bin Yeri. Nama matrix B0819100259, and we will present our project.
okay. So for the introduction, there are two port components used in satellite and mobile communications, radar, electronic warfare, metrology, and remote sensing system that operate at microwave frequencies of 1 GHz and beyond to give frequency selectivity. Okay, this microwave filter perform the same function as electric filter at lower frequency, but differ in their implementation because circuit dimensions are on the order of the electrical wavelength at microwave frequency. Thus, in the microwave section, distributed circuit elements such as transmission lines must be used in place of the lump element inductors and capacitor used at lower frequency. This can make microwave filter design more difficult, but also introduce a variety of useful coupling and transmission effects that are not possible at lower frequency. So the extension loss approach is used to build most current microwave filter, which approximates the amplitude response of the filter using network synthesis technique that have been expanded to handle microwave distributed circuit component. A general that procedure is followed to accommodate microwave distributed circuit element. Those procedures are determination of filter specifications, design of low-pass prototype filter, scaling and transforming the filter, and implementation, which also known as conversion of lump elements to distributed elements. Okay. So for low-pass filter, low-pass filter pass low frequency transmissions while rejecting high frequency. Frequency, bandwidth, ripple, insertion loss, and voltage standing wave ratio are all performance characteristics. The selected frequency is the cutoff frequency for RF low-pass filter. Bandwidth, the range of frequency that low-pass filter pass with minimal attenuation. Ripple is the peak-to-peak variation of the passband response. Insertion loss is the total RF power transmission loss resulting from the insertion of a device in a transmission line. Insertion loss is the ratio of signal power at the output of the inserted device to the signal power at its input. VSWR is a unitless ratio ranging from 1 to infinity that expresses the amount of reflected energy. A value of 1 indicates that all of the energy passes. Any other value indicates that a portion of the energy is reflected. VSWR can also be expressed in terms of decibel. So for high pass filter, this filter pass high frequency transmission while rejecting low frequency. The stated frequency is the cut-off frequency for high pass filter. Bandwidth, the range of frequency that high pass filter pass with minimal attenuation. Ripple is the peak variation of the passband response, and so on. Same as low pass filter.
So, start with bandpass filter. RF bandpass filter are active or passive circuits that allow signal from one frequency band to pass while rejecting signal from other frequency. Most popular form of RF bandpass filter are surface acoustic wave SAW filter, crystal filter, and cavity filter. Perform a specification of bandpass filter includes specification frequency, bandwidth, ripple, insertion loss, and voltage standing wave ratio. Bawah. So this is the kata sikit. Okay, so this the graph that show that in a bandpass filter we have high and low pass in the same graph. So next, for Lampert design, the word T and pi are used to denote a Lampert element filter or Lampert design. As demonstrated below, T elements begin with a series elements, but pi network design with a shunt element. T resemble as a letter T, while pi resemble as Greek letter pi. The figure below show for the three-pole network, all number of poles still resemble the T and pi letter somehow. But for even numbers, the distribution is nearly lost in a T network. Would start with a series element and ends with the shunt element. Okay, first start with figure 4, that T network, and figure 5 with pi networks. So down more. So this the place that we want to find the what we call this uh, normalized frequency for maximum flex filter prototype. This for the maximum flex filter for table. The same, this for 0.5 dB Rippler. Now this for its table. And this for 3 dB. And the table. So this formula used for low pass filter that want to find in using maximum flex response. So Ck equal to Gk Ro omega C and Lk Ro Gk divided by omega C. But another one for the shunt capacitor, Ck equal to Gk divided by delta Ro times with omega C, omega naught, and Lk equal to delta Ro divided by Gk omega naught. Another one, this is for serial inductor. Ck equal to delta divided by Gk Ro and omega naught. Lk equal to Gk Ro divided by delta omega naught. So distributed element filter design. So this is the element of the circuit which are not localized in discrete LS, CS, and RS. As a result, distributed element field can be designed to tight tolerance, which make this approach a better fit and higher frequency application for distributed element filter design, transmission line, and waveguide are the primary methods used for transferring electromagnetic wave around the circuit. Simply put, the transmission lines is a two conductor structure, and waveguide is single conductor with the hollow metal tube that provide distributed inductance with the empty space between providing distributed capacitance. So this is the figure. So more. So start with our project. So first is our low pass filter circuit, the circuit that we design, and then we want to find the distribute. So we design another circuit, and we got the result for low pass filter distributed circuit. And next for the band pass filter, Lambert. So this is the circuit for the band pass. So result, continue.
For the calculation for the low pass filter, as the given information from the patient, we got insertion loss at 55 dB at 3.4 GHz, and the cut-off frequency is given 2.4 GHz. So from the information, we need to find the omega over omega c, that is frequency minus 1 to get the so that we get the value of n. We need to find the value of n. So we use the attenuation table again versus normalized frequency for maximally flat filter. So from that graph, we get n equal to n, and this value G1 until G11 is given from the table of this table. I will show you the table. This is the table for maximally flat filter. So we got the value 10. So we have 11 value of G. So from the value, we need to calculate the value of each capacitor and inductor. So this is a pi network. I create a pi using pi network, starting with the capacitor. So we just key in the value of G into the formula G1 over R0 omega C. So for omega C, we use 2 pi Fc, the cut-off frequency, which is 140. And for the R0, we assume the R0 as 50 ohm. So after we key in all the value for the capacitor, this is the value that we get. While for inductor, we use the formula of R0 G2, R0 GK over omega C. So this is the result. This is the value that we get. Okay. Next.
Okay, so for the circuit, we design with follow the low pass circuits. So starting with capacitance, 5 capacitance we use and 5 inductor we use. So as the result, so first M2 is equal to the cutoff, which is 2.4 GHz, and M1 equal to 35 dB. So which not exact value, that is 3.4 GHz, but actually we get it near. So next.
For the next part, for Richard transformation. Okay, firstly from the circuit that we created, we need to transform the circuit into Richard transformation. So this is the shunt step, and this is the series step. So this is open circuit. This is the short circuit, and this is the open circuit. This indicates the inductor, and this indicates the capacitor. So to find the value of the shunt step, we need to use the formula of 1 over GK. So this is the value that we get, and then the value of the inductor, we just take the G value for inductor, each inductor. So that is the first step, transform Richard transformation, and then the second step is to implement the Kuroda identity. So this is the implementation of the Kuroda identity, and this is calculation. Okay. Next step, we need to normalize using the core implementation. So for this part, we just look at this, and for the denormalize, we need to multiply with 50 ohm impedance. So next.
Okay, so for this part, before tuning, we design the circuit. Refer to the let's skip. Refer to the design that we get from again
Sorry.
from the normalized. Okay, so normalized. So as we can see that 50, 57, hundreds until 50, that is the top, and the bottom 117 until 209 in the bottom. So we follow the design. So that's the circuit that we get. So first, after we design the circuit and we using a line cut to get the W and L for each part, and we simulate and we get the result that is not a tuning result. Okay. So that is the graph. And then after we are tuning, okay. So we get the result. So first with M2 that equal to 2.4 gigahertz cut off, but actually we don't get 3 dB, we get 5. And M1 equal to 3.4 gigahertz, but actually we don't get 35, but it's almost near. So next, with the bandpass.
Okay, for the calculation of the bandpass filter, the question gave the center frequency, which is 2.4 gigahertz, and the bandwidth 260 megahertz, and 0.5 dB equal ripple with n equal to 3. So we referring to the table of 0.5 dB ripple, we get 4 key values. So we just use the value into the formula. So to find F1, we need to use the formula of F0 minus bandwidth over 2. So this is the value for F1 and this is the value for F2. And for the delta, we need to use the formula of omega 1 minus omega 2 over omega 0. So this is the formula. And then we need to find the value of each capacitor and inductor based on their circuit type. So they are parallel and series type of circuit. So we need to use the formula accordingly. This is the value that we get for each capacitor and inductor. Next, I will.
Okay, so after we calculate that, we use circuit follow that pi network. So this is following the pi network, and we design the circuit for the bandpass, and we put all the calculation result into the inductors and capacitance, and then we get the result for the bandpass. So this is the graph. So first, M1 refer to 2.27 gigahertz, which means F1, and M2 equal to 2.53 gigahertz. which is F2.
For discussion part, in the low pass filter design, there are two types of design that must be implemented, which is the lump design and the filter design. The lump design circuit is determined using the insertion loss approach. Because of the filter is maximum flat, the number of orders of the filter is calculated using the attenuation and the normalized frequency graph and the maximum flat level. Following that, we get the value of the N and the G value, and then from the value of G, we get the capacitor value and the inductor value. After that, we continue on distributed design. We use the formula to transform the circuit picture, and then we utilize the thermal identity to transform the shunt stub to a series stub. And then the low pass filter is then used to get the normalized impedance from the start. Then we denormalize with 50 ohm impedance. Next, we insert the implementation in the ADS software using the denormalized value. We employ the software line computation with the help of M sub setting. And then we synthesize with the parameters provided, and then the L and the value of W pop. The graph is then plotted, and then we use the tuning method to get accurate value. The tuning only done at the line of each MLIN and MLOC. Finally, we are able to get 5.162 dB at 2.4 GHz. Next, we create a lump circuit for band pass filter. With the given information, we determine the F1 and F2 frequency using the center frequency, and then from the value of N, we get the value of G, and then the shunt capacitor and series inductor calculated using the formula, and the desired result was obtained.
For the conclusion, finally, we performed all the manual calculation to arrive at the final result. The unoptimized result were displayed alongside the optimized and circuit simulations. The lumps distribute LP, distribute LP, and distribute BP among the design mentioned.
So that's all from us. Thank you.